How's everyone doing? Hope you're all doing well. Welcome to Chapter 3. This is our very first lecture video for Chapter number 3. And this is going to be our first real chunk of actual chemistry that we're going to be learning starting today with this video. As you guys obviously know, you just finished up your quiz for Chapters 1 and 2, and that was pretty math-focused, right? There wasn't a whole lot of chemistry involved in that chapter. I guess you could say a little bit with the density stuff, but that was heavily related with the lab that you guys have just been recently doing, labs 1 and 2. But this is going to be our first chunk of actual real chemistry. Now, Chapter 3 is titled Matter, Properties, and Changes. It's going to be some pretty baseline stuff, and a lot, if not all, of the concepts we learn throughout this entire Chapter 3 here are going to be concepts that come up multiple times throughout the rest of the school year, between really now and even as late as May and June. So this is going to be some pretty baseline stuff that's going to help build the foundation for what we're going to be continuing to learn as the school year progresses. So, plain and simple, I know we've already done this, but we've got to redefine this idea of what chemistry truly is. So, chemistry is the study of matter and energy. Pretty straightforward, but a lot of that is encompassed in so many different things. Matter and energy can be broken down into so many different things. So let's try and do that. Matter, as you guys also know, because we kind of brought this up back in Chapters 1 and 2, matter is anything that has mass and takes up space. So like I've mentioned before, matter is essentially the combination of two things that you're very familiar with: mass and volume. Right? As soon as you have mass and volume associated with one given object, if it has mass and it has a volume, that is consistent of matter. Now, this word substance. Substance is used so frequently in the realm of chemistry, and the actual basic chemistry definition of substance is matter with a uniform and unchanging composition. Again, matter with a uniform and unchanging composition. And when I say these words, uniform meaning same throughout, right? Think about the fact that to a degree, us here at St. Joe's, we all kind of wear uniforms, right? If we're wearing our St. Joe's polos, we're all relatively looking the same throughout, right? On our days where polo season is over and we're all wearing shirts and ties, again, relatively same or uniform throughout. States of matter. These are ones that you guys are, should be relatively familiar with. Of course, solids. Now, each of these, I'm going to kind of define them all individually. So solids have a definite shape, and they also have a definite volume. And we're going to kind of use this idea of volume and shape kind of spread across all the three different types of states of matter that we're going to discuss in this class. So again, solids have a definite shape, and they have a definite volume. Think about my mug here, right? I can't really do much to this coffee mug here without breaking it. I can't really do much to this coffee mug to change the shape or the volume of this thing, right? The shape of it is relatively cylindrical, right? As we all know. Okay, you guys have seen me, drinking out of this in class. It's relatively cylindrical, and it has a very specific shape as well as a very specific volume. The volume inside of this cup is just about 20 fluid ounces. Okay, so it has a very definite shape and a very definite volume. Other than breaking this thing, I can't really bend or break or smash this thing in a way to change that shape or change that volume. Now, when we think about our next state of matter, liquids, that kind of changes a little bit. The volume stays definite from a liquid, but what doesn't stay definite is the shape of that volume, or of that liquid rather, right? And this kind of makes sense, right? If I have 20 fluid ounces of water inside of this mug, for example, if I pour this water out into a graduated cylinder that can measure fluid ounces, it's going to pour up to 20 fluid ounces, right? So it's a very definite volume of water, right? If I have 20 fluid ounces in here, I've got 20 fluid ounces in here, right? Nothing's going to really change that. But what changes is the volume, or rather the shape of this liquid, right? This liquid right now, if it's inside of here, if I have 20 fluid ounces of liquid inside of this coffee mug here, this is going to essentially take the shape of my coffee mug here, right? But let's say I turn it over and I pour it on the floor. Well, although I still have 20 fluid ounces of liquid on the floor, it's now taking the shape of the floor, right? So the shape of liquids is entirely malleable, right? Think about, again, inside of my water bottle here, right? I have a bunch of water in my water bottle right here, but as soon as I pour this out, right, it's no longer going to take the shape of the water bottle. It's going to take the shape of whatever the next container is, okay? That's liquids. Up next here is, of course, then gases. And this takes a step totally in the opposite direction of both solids and liquids. They take the volume of the room or container as well as the shape, okay? So it's even one additional step past liquids here. Solids have a definite shape and a definite volume. Liquids have a definite volume, right, that can't really be unchanging, but they take the shape of the container, right? So their shape is not definite. It's based on whatever container they're in. Gases run into both scenarios. They don't have a definite shape, and they definitely do not have a definite volume either. So they take the shape and the volume of whatever container they are in. Vapor is a form of gases from a substance that is solid or liquid at room temperature. So vapors are a little bit different than gases, and again, that they are essentially gases that form of a substance that is either a solid or liquid at room temperature, okay? So they're still under that same realm of being a gas, but they're just defined somewhat differently as a vapor as opposed to a true gas. Next up is physical properties here. So physical properties can be observed without changing the substance. So when I think about and talk about physical properties, it's going to be things like the color of a substance, the temperature of a substance as well, density of a substance, right? So if I have a specific substance in front of me, without really changing the substance at all, I can still observe the density of it. If that substance has a particular odor, for example, right, that odor is going to be, pretty consistent with the physical property of it. The melting point is another one. The boiling point as well, and its ability to conduct electricity. So all of these, color, temperature, density, odor, melting point, boiling point, and ability to conduct electricity. These are all physical properties that we can observe without actually changing what the substance is. Switching from physical properties now to chemical properties. There's a little bit more involved with chemical properties. Because although there aren't any clearly defined chemical properties like we see in physical properties here, chemical properties essentially are more of a description of how a substance can combine or react with another substance. So it's not as clear-cut as physical properties are. Chemical properties are more so based on which substances you have in front of you and how they either combine or react with another substance. So this is going to include descriptions of what happens when these two or more substances react with each other. Right? So descriptions of what happens when it reacts with another substance. Now, this right here is just a table. I know you guys obviously have this out in front of you, but there's a lot of pieces to this table here. So this first table here, table 3.1, has several different substances here: oxygen, mercury, water, sucrose, and sodium chloride, or just that's called salt. It's got several different types of physical properties present here. It's got color, the state of matter it is at 25 degrees Celsius, its melting point, its boiling point, and its density. And again, these are all really great sources of physical properties for each of these substances. Now, this next table here, which is just below table 3.2, has the properties specifically of the element copper. Now, it's going to split. It's going to be divided between physical properties on the left here and chemical properties on the right. Let's just go through really quickly and identify properties on either side. So when you look at a piece of copper, whether you're talking about a penny or just like maybe some copper wiring or copper piping that's in your house, for example, for the most part, copper has a reddish brown and shiny look to it. It's easily shaped into sheets, which is the definition for the word malleable, and it can very easily be drawn into wires, which is the word called ductile, and that's a big driving force as to why a lot of the electrical work done in homes and businesses and whatnot are based in copper. Right, it's very good at conducting electricity, and the metal itself is very easily drawn into wires. So it's a great piece of equipment to utilize for electrical wiring. Again, it's a good conductor of heat and also electricity, like I just mentioned, and it has a very specific density of 8.92 grams per cubic meter. cubic centimeter, melting point of 1,085 degrees Celsius, which is very hot, and a boiling point of even higher than that of 2,570 degrees Celsius, right? So those are all the physical properties, kind of in line with what table 3.1 has to offer. On the right-hand side, however, are our list of chemical properties. Again, notice how these chemical properties, as we read through them, are not as clearly defined and clear-cut as the physical properties are. It's all based on what our copper is reacting with. So for this first bullet point, it says, forms green copper carbonate when, green copper carbonate compound when in contact with moist air. A great example of copper turning into green copper carbonate when in contact with moist air, you probably guessed it, the Statue of Liberty. Okay, Statue of Liberty is not actually supposed to be green. It's more of a copperish. It should be that reddish brown shiny color. But due to the very moist air of the water surrounding the Statue of Liberty, you know, we get that moist air in contact with the copper, creating this copper carbonate compound that is a little bit more of a greenish color. Copper can also form new substances when combined with two different acids, an acid called nitric acid and another acid called sulfuric acid. So they can form entirely new substances when combined with these two acids. And lastly, copper forms a deep blue solution when in contact with something called ammonia. And ammonia is in a lot of popular window cleaners and other cleaners in your household. So again, notice how it's very, very specific. It's not as cut and clean and cut and dry as the physical properties on the left, right? It's not just very identifiable facts. It's more of like a description or a story about what happens when you combine copper with some of these other items. Okay, so that's kind of the big difference between physical properties and chemical properties. Now, on to physical change versus chemical change. We're going to start with physical changes here. And physical changes are more of an action. Properties are more passive things that you look at and just identify, right? So your physical properties, things like your melting point, your boiling point, these are things that you just can determine by just looking at it, right? More passively. Physical changes are when you actually make an attempt to physically, actively alter something with the composition of your substance. So physical changes are going to include things like cutting, smashing, heating or cooling, so making sure to do that without a reaction actually taking place, so cutting, smashing, and heating or cooling. Phase changes between all the different states of matter. So even your phase changes, right, from solid to liquid to gas, and anything in between. Phase changes themselves are physical changes. They're not chemical changes. That's very confusing for a lot of you guys, and we'll talk more about that next class. But trust me, any physical change you see, let's think about taking an ice cube out of your freezer and setting it on your counter. Okay, your ice cube is made up of water, H2O. Well, it's in the solid state, but if you leave that ice cube out on your kitchen counter, for example, after 2 hours time, you come back to the kitchen counter and you see a small little puddle of water. Well, it's water in the liquid state, but it's still H2O. So the composition has not changed, you just changed the state in which it's represented in. So phase changes are definitely physical changes. So looking at each phase change individually are going to be things like boiling, freezing, vaporization, condensation or condensing, melting, solidifying or solidification, sublimation. I believe that is it. One more, sorry, deposition or deposit, right? When things deposit or deposition. And we'll talk more about these individual phase changes when I see you guys. Okay. But now moving on from physical changes to chemical changes. Again, this is, more of a active thing, right? Not as passive as just identifying something like the green copper carbonate compound on the Statue of Liberty, right? This is more of an active thing, a process that involves one or more substances changing into a new substance with a totally new composition. Well, essentially what I'm saying is, if what you start with is not what you end with when a change occurs, that is what's referred to as a chemical change. So if what you start with is different than what you end with, that is a chemical change. And this is going to include things like decomposing, right? Think about things in the forest dying and decomposing, exploding, corroding, rusting, tarnishing, and fermenting, burning, and yeah, that's it. Okay, fermenting and burning, right? So all of these are great examples of actual chemical changes that can occur from certain objects. So again, All of these are going to represent a change from one thing to an entirely new substance after that change has occurred. Okay. Thanks for watching, guys. I'll see you in class.